Hello. I think we should just get started here now. I'm sorry I'm starting about, well, only 1 minute late, so that's not bad. Anyways, we are gonna start with, I've picked a bunch that are from the uh, Art of Electronics textbook instead of go into one of the other two textbooks that I do have. I decided to stick with that one. We are gonna do um, from page or figure 2.96 from page 125. They have this circuit. Now it's just a regular old transistor. Um, yeah, PNP transistor. I think that's what. Yeah, they use PNP transistor. And this they just had symbolized by a load. Now they say it is a current source exercise. So I'm guessing they are wanting us to figure out what's going through this right here, this current right here. So it would be my guess, again, I'm not entirely sure, but that they are wanting us to find what current would be going into the base and driving this here. So if we say, okay, let's just say, well, we have a, let's just bump this one up to 1.8K just to do it in our heads here again. So this would be 10K in total here going to ground on 10 volts. So that means that this here would be 1 milliamp traveling down this circuit, or this part of the circuit right here. It's going into the base. Now they say to have, no, I see what they're doing here. Okay, yeah, we can disregard what I just said more so. So what they are doing is they're gonna say, okay, there's 8.2 volts burnt up here. So that means that there's only 1.8 volts or so here. So we would lose about a diode drop here. So it's 0.6 volts. So 1.8 volts, 1.2 volts. So we would have just under a milliamp here. Yeah, almost three quarters of a milliamp would be going through here. And that's all based on, okay, we know the voltage at the base. We know that there's about a diode drop between the base and the emitter voltage. And we also know what this value is. Okay, I think that is what they're getting at. So this will be 3/4 of a milliamp, which means that this will also be dragging 3/4 of a milliamp through it. Let's see and try it out here. So we got, yep, well, a little bit less, 684 microamps, which happens to be 0.68 milliamps. And here we have 1 milliamp almost. And here 1.623. I think I said 1.8. Then down here we have just 1 volt there. Yeah. So that is about what I had thought. Guess we might as well move on to the next. Okay. Which will be .28 on page 147. Guess I decided to go right into the MOSFETs here, because that's the one that I just did was MOSFETs. The lab on learning the art of electronics, which is yet a different textbook. No, there's so many textbooks, eh? how can one ever pick their favorite? Okay. Yeah, we're at 1.47. Figure 3.28. Oh, there's two here. Okay. Common source amplifier. So let's stop this. And then we will just delete this out here. And let's just draw up this circuit here. And, yeah, so they both have a capacitor. There, capacitor there. Resistor. And feel free to comment or request any different circuit. Preferably, I think this is N-channel ones. Yeah, I'm guessing N-channel is the most common, so we'll just try that. I might be wrong. Who knows? I'm wrong sometimes. I'm wrong a lot, actually. Again, like I had said in a previous live, I'm thinking of doing a version of this where I instead of like just simulating these circuits, I'm interested. I would try setting up a breadboard view and a non-breadboard view, like just a view of me, and like so like I could build the circuit on here, and then also build the circuit on a breadboard and just test it out, and then you can see the output of that. So this, now we just need a wire here. So we'll do the one on the right side of it first. Actually, no, we're not. Yeah, I didn't decide to do this one. So now we have to go and draw that resistor in. I'm sorry I'm making so many mistakes at times here. If you've been to any of these before, you probably know that I do that. Yeah, so we'll draw now just a voltage source. So here we go inputs and sources. We want a one terminal voltage source. We'll just put that in there. Then we have to draw in all the grounds here. So now we got the grounds in. Let's draw some sources. Voltage source, two terminal. Then where does it say is the out right here? So let's add a output and label. We'll add a test point. We've put the view and scope here. So now, common source amplifier and source fault. So I'm guessing this is the common source amplifier. I'm actually not entirely sure. I don't think I've actually made this. Oh. One second, I just realized I put the whatchamacallit, the category was gaming, and this isn't gaming. You said I switched it to education. I don't know why I did that. Oh, thank you. Here, I'll type that in chat. Yeah, so let's just look at this circuit here. So first things first is that this common source amplifier source follower. So this here, one thing is that these gates are very high impedance. So this capacitor will only discharge through this resistor. It's not going to discharge anything into this gate. I'm not sure if that's important or not yet, but possibly it is. I don't know. But when we apply this 5 volts here and this capacitor charges up, eventually what it will do, it will let this flow in here. Eventually we'll charge up this capacitor as well, and there will only be 5 volts here. Let's just run this. Well, yeah. Yeah, so you see what happened. Because, yeah, we just quickly reached an equilibrium there. Let's go edit. Put this to 10 volts. Apply. Okay. Let's change this to a... delete. Let's change this to a... inputs and sources. Square wave source. Just curious. Yeah, so you see what's happening here. I don't know if that's what they intend this circuit to do, but what is happening is when we apply, so when it goes high here, then this capacitor quickly charges up and settles at that 10 volt mark. And then when we turn back and go negative, it falls down to 0 volts quickly. Let's just slow down the simulation speed. We'll watch this for just a second here. I just want to see how fast it goes. Yeah, so now this is discharging through here. But not very fast. Oh, I see. That's why I was thinking of this wrong. So this was, like, when this gets turned off, that means that this goes high. Yeah. I just read this a second. JFET amplifiers. I think I'm going to mark this as something that I'm going to look at later. The common source amplifiers follower. Yeah, I don't think I didn't really provide much information right now. But that's one of the reasons why I like to do this. So I like to be able to just look at a circuit, try to explain it, and then if I can't really explain it well, look at it later so that I can learn about it more. So let's go to the next one. So 3.36. Into the JFET differential amplifier. So let's do that. Active components, JFET. and JFET. Probably don't need to be that big. Yeah, there we go. Now, we'll draw resistor in here, resistor in there. Doesn't give us a value for them. That's fine. We can just make up values. I think it wants test point at both these places here. And has one more resistor. But yeah, one of the other benefits, if I do start doing stuff like this over the breadboard, would be that you'd then be able to I'd be able to look at more complicated circuits and have a larger variety of components. Because on this, it's a really good simulator, but the thing is that there's only a certain amount of components that it can actually provide. So let's go here, edit. Volts, we'll say. Then here, we're gonna put this one there. Oh, hello. I'll just type hello in the chat here too. Yeah, a few of these circuits, I was looking at them earlier and I was like, oh, I wonder if I should do them or not. But that's why I'm here to learn too. While I find it very a very good learning experience to try and explain a circuit to somebody, or when I feel like I'm explaining a circuit to somebody, as sometimes there's nobody to watch, but you know what I mean. It's very fun, and yeah, and it's nice. Sometimes I like just picking out random circuits and being like, oh, what does it do? Why does it do that? So let's put those two. Edit. Oh wait, cancel. We'll just put them both in the scope. View scope. So you see, oh, they're both called the same. How about let's edit, label, cancel. Can I change its name? Voltage test point. Nah, whatever. Okay. Okay, so now we have this. Given that, what does it call it? Simplest JFET differential amplifier. So that's why I put these two at a different voltage, because I think when they're different here, this one here is going to turn on more, and it's going to pull more current through than this one here. And then this one, how will that work? I'm pretty sure that is what will happen here, is that this will pull more current through here. That means that this voltage will be higher. That's right, because yeah, if we have a more current coming through here, then the voltage will be higher. Nope. It should be the same. Let's just try it here. Yeah, no, this voltage is higher. Oh, where am I from? I am from Canada. Saskatchewan, Canada, to be specific. But there is definitely more current coming through here, through that one. Why would that be happening? Yeah. Like I said, I just did this lab, so I should know. But that was mostly, MOSFETs to give me the benefit of the doubt. JFETs, it actually didn't cover that much. The only time when we had a JFET was one time when we built a homemade op amp. There was a JFET there to give a high impedance current source. I just don't, because this gate, because that should be a high impedance input right there. Yeah, it's put it in 10 milliamps. Okay. Think I see why. So, this here means that this 5 volts, if I understand it right, we'll see. Means that there should be 5 volts right here too. I'll have to go back and look, but that's what I'm guessing. Or okay, yeah, about a diode drop. So yeah, about a diode drop there. So that means that 9 volts has to be passed through here. Now, at this point over here, we only have right. So these two are at the same voltages. Well, let's just see. Yes, 5 volts. Yeah, the left one. Yeah, it should be at 5 volts. It's showing a diode drop, but so it's dictating it. I'm just going to change this to 3 volts. And now it should be like 2 volts less than it is now. That's what I'm guessing. And yeah, now we change and we take the current from this side of the circuit. Okay, that makes sense. You see, that's the other thing I like it too. When people watch my videos or and watch me, who are actually more knowledgeable than myself, because then I can learn more from them as well. That's always fun. So now I think I do understand what's going on here. I didn't before. The current in the 1K. Oh yeah, the current, yeah, it doesn't change, yeah. Yeah, that's why both of these are pulling in. Like this is pulling in some more current now. Before, this one wasn't pulling in any current. Oh, it's pretty interesting. And that's 3.46. Yeah, so I'm gonna just change this. Yeah, I think there, we'll change that there. Apply. Yeah. Oh, it's a little bit more. It's about a milliamp more, but not much. Oh, that's interesting. Well, thank you. I think I got this circuit. I think I understand what's going on in it pretty well. It's a very interesting circuit. I made a current mirror when I made it during the Lab 5 of learning the Art of Electronics. It actually, I didn't actually use the JFET version that they asked us to make, but I made one out of bipolar junction transistors because I didn't have the JFET that they requested. So. But I think we will go to page 229 and do 4.12. But yes, I am. It's amazing how much you learn. Well, I'm learning so much in this. I'm trying to do all those circuits or all those labs and learning the art of electronics, and it's amazing how much stuff is in there. And then like this the art of electronics is its companion book, and has even more stuff. Oh yes, now we go back to op amps. Okay. I'll just delete this out now. But yes, thank you for all the chat today. The first ones I did didn't have pretty much any chat at all. So it's really nice. I do like talking to people. Let's do the 4.12A. So I'll again like I've done. Yeah. Yeah, that's for a constant current. Yeah, that is. I do. It's interesting. Like I remember during my first what's it called uh electrical engineering classes at university. They told us that, oh yeah, current sources aren't really used or blah blah blah. And then I learned here in the art of electronics, it's like, oh no, current sources are used. They're like they're basically everywhere. Like they're one of the main things that are in an op amp, differential amplifiers. It's very cool. And they're very useful circuits. I don't know why. I remember that. Maybe I'm misremembering, but it's for some reason I remember them saying that, and now I'm like, what? They're very useful. Oh, that's wrong. I have to go. This is a PNP transistor. Active components. PNP. Short OPV. I'm just reading the comments here again. Short OPV. Interesting. I also, since you're from Germany, I actually have went to Belgium, which is near Germany, not Germany. I did go to Oktoberfest while I was there, which it was very fun, and I'm actually I'm quite enthralled with beer and such too, as well as electronics here. Um, if you can see, it's become sort of a tradition that during this thing, I've actually I'm drinking a beer for throughout like the whole live stream. Just I don't know. I did that the first time, and now I do it in the other times. Um, it's not the best for learning, maybe, but I usually do these later at night, and it's good. I do brew my own beer as well. This isn't my own beer. Operation Varstocker. Oh, I don't think I can pronounce that well. Um, So again, this one doesn't have the values in that it wants us to use. It just has the components. Yeah. And the components, like, so we have these resistors here, and then, so it has VCC minus VN. So VN would be set by this, so we will set VCC with a inputs and sources, voltage source. There, 5 volts. Oh, let's stop it. I want, yeah, let's set. Before I, well, I'll just say thank you again in the chat. Yeah, before I start it up, I just want to try and understand the circuit. It isn't just simulated stuff it's okay, but I find that it's always good to. Oh, in Nuremberg, I went to a Nuremberg Ice Tigers game one time. It was very good. I liked it. When I went and I was traveling around Europe, I went to a whole bunch of hockey games, which I know is a very Canadian thing to do. But anyways, so I set this as the load, which, I mean, any load, it doesn't really matter. I always set it, but that's not really what we're looking at, right? Now, what it does is that it says that we can calculate the current, the I load, so the current of the load right here, using the formula VCC minus VN divided by R, which this is R here. So, then this would be 2.5 volts. And, yes, I think I see what it's getting at. Right? Because, yeah, that would be VCC minus VN divided by R. Yeah. So I see how it's getting there to that formula. So let's just go through this example. So we have 2.5 volts here. Well, this minus wants to be at 2.5 volts too. So since it's at the non-inverting input, or yeah, that's the soccer team, yeah, or football team, yeah. I watched. I was in Brazil once, and I watched a lot of soccer, but not since then. But anyways, so this is gonna try and get, like, this output's gonna try and take this inverting input to the 2.5 volts that it sees here. The way it will do that will be that it will keep outputting high, like it's going to try and put a higher and higher voltage until that is satisfied. So what it should go here, I'm guessing, will be about 2 volts. And I get that because from here to here will be 1 diode drop, but ground's over there. Yes, I like ice hockey more than soccer. I like Canada is quite well known for its hockey. I know it might not look at it because I don't know if you know, but there's a World Junior Championship on right now, and we lost, and we are all very upset about it. But yes, I like hockey more. Yes, so, oh, here, let's say, thanks. I like my stream too, because somebody just saying that they would stay and watch, but they have to go. But yeah, I like this stream too. Yes. So where was I? Yes. So we would have this op amp is going to push this output up high until such time that this is at 2.5 volts, like this one. That will mean that we will have to drop this amount of voltage, like from 5 volts, whatever's dropped across here, and then the current going through will be that. So like that is VCC minus VN. So that's this one here. And then the current will go just from our V equals IR. Yeah, so it will be 2.5 volts divided by 1K, 2.5 milliamps going down here. Now let's check it. So we got 2.5 milliamps. Now, oh yeah, because this would be now why would that go there? I would think that it would be the same, but we've went down to only 1 milliamp. Wonder if it has. If I go, oops. Let's just go here. Yeah, so now we have 2.5 milliamps. So it has something to do with the with that resistor there. I guess it's probably because this, yeah, so this current, I would have thought though from the way that they worded it, that it would be a constant current. But I guess not. Oh, well, thank you for watching anyways. You have a good sleep. It was nice talking to somebody from Germany where I really loved my time there. It was great. Uh, yeah, but we are pretty close to that. You see, you just had to get the 2.5 volts. Up there, and then it satisfied our op amp golden rule here. Now, the other thing to keep in mind is that we're using a perfect op amp, which means that this is truly no difference in voltage here. It will try to do its best to get there, but most op amps do have a bias, a voltage offset. It's usually in the microvolts, but it is there. It's just something to keep in mind. So, I think I got that one pretty good actually. Op amps, they were so mysterious to me for a while. That could be that I'm adding here. Let's go back and add in that resistor. It's just I thought the way that it looked, but yes, I would say that oh, that's a wire. Draw add resistor. So yeah, we would have 2.475 volts there. Yeah, because they're divided in between each other. So, but yeah, I just don't get why. Why they worded it the way they did is what maybe I'm just reading it wrong, but they worded it like, okay, the current going through this load right here. They just put a big like rectangle around it and said load. Would be like that equation. But I think you're right. Like, so we know since this is going to be there, then that means that this will be like that 2.5 volts, basically the same as over here. So that would mean that add in this extra resistor, and then what it is this LED, I think, takes it down. So it drops 1.5 volts, it says. So we got 1.5 volts, and then the rest of it would be dropped on this resistor. So then you got 1 volt basically, and then that's how you get to a milliamp. It's 921 microamps. I'll have to think about that. I think maybe it's just saying if we just put a voltage, or not a voltage, like that diode LED there, then it just gives that. Yeah, it must have something to do with the extra resistor. Well, it does have something to do with the extra resistor. Anyways, I'm going to move on to the next circuit. That circuit is 4.16 on page 30. Page 230, I mean. Yeah, just a simple integrator here. That's a nice change. I picked all of these before I came down. I was actually watching a TV show called Anger Management. It has Charlie Sheen in it. And, well, I just picked ones that stuck out to me. That's why some of them, I think I picked them just because, I don't know, I wanted a bit of a challenge today. I mean, some of these circuits I'm sure aren't a challenge to some people, but some are definitely a challenge to me at times. Where are we? Yeah, there we go. So now we go this one, add ground. So here, I just wanted to, like, I think the reason I picked this one is because I think I understand it, but it's always nice to redo them, just in case I didn't. Yeah, I have that stopped. I think I do, right? Okay, good. I got it stopped. Because, yeah, once I put it in, it's going to give it right away. I don't want that. I'm going to slow the simulation speed right down. Draw a test point here. Inputs and sources. Where'd my test point go? Oh, wait, it's outputs and labels. That's right. The other thing that I like about this is that, like, you know, when I do these streams, then I get to learn a lot about, or not maybe learn, but I get to go through the motions a lot of making circuits in the simulator. And it can do that a lot faster later on. But anyways, let's just think this one's through. So what's going to happen is that this 5 volts is going to be applied here. Now, no current will flow into this input right here because of our golden rules. So that means that this will go and will charge this capacitor. Now, when it charges that capacitor, this voltage difference will increase. And since this is the inverting input, that means that it will start driving this down, trying to drive this down, but we have no feedback. Now, what will happen then, because this is just a solid 5 volts, it is going to be driving this down just steadily till it hits its bottom. Let me just think for a second here. Because what they call this circuit is an integrator. I'm just trying to think about why. Because if it's going down, I don't think that's right? Because it's an integration goes this way a bit. Going down would be minus 5 volts. Oh, let's try it here. Yeah, see? But right here, we got V. Here, I'm gonna just horizontal scale. We're gonna just decrease it. There we go. Okay. So now, there we go. So we got a thing like that. Now, why would that be? So I'm trying to think. I put that together wrong, maybe? No, it has the... Let's change this to minus 5. Okay. So now it's going to go up. Just trying to figure out why. Thinking to myself again. I should verbalize my thoughts, I guess. It's just that. So, here. I will just draw. I think I can draw a line here. Where is it? Maybe I can't. I'll just draw a wire then. So, this is plus 5 volts to me. So, like that, we're a positive slope. And since this is an integrator, and we're applying minus 5 volts, I thought that we would have this. But I think yes. So I think, yeah, it's just, it does say that later. I'm just misconstruing it. Like here, let's stop this here. And let's do the opposite. No, this is just going to be really messy. Actually, yeah, right there. I think if I go here, I should go like this. And then I'll draw another. Well, here I have a wire right there. Now, if I'm right, hopefully I'm right. Oops. Sorry, this is just going to be a horribly looking circuit. Now if I'm right, it will act the way that I think it should act. Oh, wait. what's this? Control Z, Control Z, Control Z. We're just gonna move it back here to where it was. I think I'm gonna just think about this. I might read the textbook a little bit on this page too. Because I did sort of explain what it would, but I think I just misunderstand how they define an integrator. I'm thinking too much in calculus, I think. Just say look at later. Then I'm gonna do one more circuit here. Page 234. Page 234, 4.25. Yeah, 4.25. Right down there. And draw. I always forget, I need to try to keep talking during these things, or else you'll all get bored. Which, I mean, I don't have too much trouble talking. Just sometimes then I start mumbling to myself, and I forget that I'm actually assembling a circuit and stuff like that. Which also isn't good because you all are here to see me assemble a circuit. So I have to remember to do that too. I'll just drag this over here. Think. Oh, oops. Da-da-da-da. Da-da. And so it has very specific values for this one, so I'm guessing this is a somewhat precise circuit. Let's just see. Yeah. So I'm gonna put that there. And this will be the input, I'm guessing. Oh no. Put it here. Yeah. So let's just go inputs and sources. Let's put a square wave on it. Just see what happens. You know, square waves are always fun. Okay. So, I'm sure that you've heard me say this before. Especially since I've done a couple op-amp ones here. But, so these two inputs always want to be the same. So when this goes up to, what does it go up to? 5 volts. That means that, oh, I forgot to put in my grounds. Oh, that's not what that means, but I did forget to put in my grounds. So let's put those in very quickly. And then, we'll go back to this here. So, say this is at 5 volts, that means this wants to be at 5 volts. Now, this is going to do all it can, like this output is, it's going to do all it can to push this up to this input up to 5 volts, which the way that it's wired, it does that by basically trying to shove more voltage up. Like it tries to raise the voltage because it's the non-inverting input that we're applying that 5 volts to. So this will go all the way up. I think it can go up to 15 volts, but probably won't get there, I think. Because once we have 5 volts there, no, it might there because we will be blocking. Yeah, and then we'll be having more current go through here. Then at this point, what would we need here? Well, we would need. So at this point here, we would need. Well, it's basically, yeah, if we had, say, 6 volts here, then that condition, no, that condition wouldn't be satisfied. We'd actually have to have quite a bit of volt, because I'm just looking at this, thinking of these two resistors together. We'd have to have quite a lot there. Let's just try this here. Run stop. Max current exceeded. That's what I thought. Oh, I didn't think that necessarily, but okay, reset. Let's just put in a very small voltage apply. Okay. Now we're on stop. There. Ooh. Reset. Unstop. Think if we should put. Oh, I think I know what happens. Okay, we will. Pulse. Put a pulse there. Okay. Convergence failed. Here, let's just try with a voltage, just a regular voltage source. Yeah, max current exceeded. So now let's edit this. We'll go 0.01. Apply. Okay. Reset. Run. Convergence failed. So I don't think we're going to be able to really get this one very well either. This might be one that would be interesting to assemble. Huh. Let's just put a resistor here. Because what it looks like is that this... Yeah, so this is put in at 1.6 volts. Let's edit this to go only 1. Apply, okay. Yeah, so that's all we really needed. It just needed some there. Let's edit this to go back to 1 volt. That's a lot of amperage though. I see. I think this needs to go 25. There we go. So that's one of our problems here. This was lower than this over here. So like this is a perfect op amp, but still it has a max output. and a min output. Now this right here, we should have at least above, okay, I bet now it would work. Yeah. So that's why. It was because this was starting to output more voltage than this was, or this had. So that means that too much current, like, was basically a dead short going through there, and that's what was causing all of our errors there. Now, yes, 9 millivolts. Yeah, so this is basically a 10 times amplifier. Yeah. Yeah, that's actually what it is. I don't know why it took so long for me to get that one. Yeah, because we applied 10 volts here. And just imagine this isn't there. So this isn't actually here, this 1K. And this transistor isn't here. We just start connecting right to here. So that means that there's going to be 1 volt applied here, because we have to have 1 volt there. So if there's 1 volt applied here, then there's about a milliamp going through. It has 1.1K, and again, I think that they're getting to. I don't really read the part on these, like the text around these circuits before I do these. I may have read it at a different time, but I don't actively read it before. But anyways, we would have about a milliamp going through here. That means that there has to be a milliamp going through this 10K, because no current flows into the inputs of op amps. So that means that we have 10 volts here dropped across there, and then that means that there's about 10 volts here. So if there's 10 volts here, that means there's 10 milliamps going down here. But yeah, so I think after a few rocky circuits there, and thank you for everybody who watched. There was a lot of activity in the chat. There's Mike Jones, the Matthias Conrath. Sorry if I didn't say his name right. He was the one from Germany that I had talked to for a while there, and Shine Affinity, so who had left earlier. But yeah, thank you for everybody for watching. I do intend to do these every Friday. It won't be next Friday we'll be doing one, because next Friday I'm actually in Las Vegas. So I won't be doing a stream. But every other Friday at around the same time, 8 p.m. Saskatchewan time, I'll be doing one. So thank you for attending, and I hope you have a good night.